Also, here as well, the length of the longest decreasing subsequence starting here and the length of the longest decreasing subsequence starting here is the same. So J. Okay, why is it, we've shown by the pigeonhole principle that on the assumption that our theorem is false, that there must be two elements in the sequence with the same ordered pair associated with them. Why is that impossible? Well, maybe you just kind of see it already, right? Because all that matters is which number is smaller, which number is bigger, which number is smaller. So here we go. Let's start with the i's. If the longest increasing subsequence starting, let's do it this way. If x sub j is less than x sub k, that means that this number is smaller than this number. If this number is smaller than this number, then looking over here now to this I, what is the significance of this I? The significance of this I means that the longest increasing subsequence starting here at the kth element has length I. But in fact, x sub j is less than x sub k. So on the assumption, here's where we are now, we're on the assumption that x sub j is less than x sub k, then this number is smaller. But if the longest increasing subsequence starting here is I, then by simply prepending, so sticking in front of that subsequence, the element x sub j, which on our which we're temporarily considering to be less than x sub k, now I have a subsequence of length I plus 1 starting here at the jth element. In other words, I have a subsequence starting here of length I, so now just stick this number, which appears earlier in the sequence and is in fact less than x sub k, onto the front of it, and that indicates that this number would have to be I plus 1. There would have to be a subsequence of length I plus 1 at least, starting here, and yet this is an I. So that leads to a contradiction. And on the other hand, now consider that x sub k is less than x sub j, which is just another way of saying x sub j is bigger than x sub k. Well, if x sub j is bigger than x sub k, now, once again, go here to this j. What is this j telling me? This j is telling me that the longest subsequence starting here, that is decreasing, has length j. So there's the longest decreasing subsequence starting with this element has length j. But this guy is bigger. And these should be d's. That makes more sense with my notation. D's and d's. These two have the same, we assume that these order pairs are the same. Why is that a problem? Because when I'm here, the longest decreasing subsequence starting at this spot is a d, and yet this previous number is bigger. But if this previous number is bigger, then once again I can stick this bigger number, x sub j, onto the front of the length d subsequence starting with x sub k, and so that must mean that starting over here, there is a longer subsequence, longer than d, at least d plus 1 or bigger, starting here, because this number is bigger than this number, and there's already a subsequence of length d starting here, so there is a longer than d subsequence starting here, the one you get by just sticking this number in front of that subsequence. So that also leads to a contradiction, and so you just can't have, because the way of summarizing this in like 30 seconds is to say that because in any subsequence, given two numbers, one of them has to be bigger, one of them has to be smaller, then you just can't have two numbers with the same ordered pairs associated with them, because based on which number is bigger, you could always make a sequence which is one bigger or one smaller by sticking this number in front of the appropriate subsequence there. And yet, so the fact that you can't have a repeat ordered pair is now problematic for us, because on the assumption that this theorem is false, the pigeonhole principle says that there must be two that do repeat. So, okay, that is once again very, very inefficient, but hopefully a complete proof of this theorem.